Okie dokie. Let's see. Okay, good morning, everyone. I'm going to start with a lovely drawing, so give me a second here. Of course, so as you guys are coming in, if you guys have any questions about light in general, I'm happy to answer them. Just go ahead and put them up in the chat. Otherwise, just hold still for a moment. 3, 4, 5. Okay, cool. Alrighty. So, here we are at a concert. Something that doesn't exist anymore, I guess. But we'll pretend it was a year ago. There is our lovely performer up on the stage there. And lucky you, for whatever reason, the performer's already singing and the seats haven't been sold, but whatever. You are the very first person to buy a seat in this lovely concert. And lucky for you, all the seats cost the same. And so presumably, if you want to choose your seat, you're probably going to choose one, right up close, close up to the stage there, right? And let's say that the second person also will buy a seat that's pretty close to the stage there. At this point, after we've started buying our tickets, we're gonna see that this kind of front row area just is too crowded. It's a pretty small concert. Those seats are sold out now. And so after that, we're going to start, filling up, other areas, right? We're going to have, the third person here, fourth person here, fifth person here. Maybe we can squeeze some more in back here as well. And so on and so forth. So we're going to see that these kind of seats in our audience here, or areas of seating, whatever they are going to be somewhat the ways that electrons behave in ground state atoms. So just to finish off the thing here, my God, I don't know why I drew so many, but I'm just going to go ahead and finish off the third row. You get the idea, right? Is that, the ideal spot, the best place is right up close, right? And this is kind of, the nosebleed section way up in the back. And so we're going to see that. Let's use dark blue. I don't normally do that. This stage here is going to be kind of just like our nucleus. And these are going to be orbitals that electrons are going to be occupying. So you guys probably saw I posted a meme in Discord earlier today that I thought was pretty clever. You guys might not quite understand it, but that's okay. It kind of goes through some of the old models of how we envisioned atoms to look back then. So, first it was just atoms were just one giant glob, and then they were globs with electrons stuck in, and then you have the quintessential, science symbol where you have the nucleus and all these different, rings that are orbiting it. And then we talked about the Bohr model. That's the one that we're probably the most familiar with if you've taken chemistry in high school or whatever. And so that's the one where you kind of have the nucleus and you have these circular rings around it. which represent energy levels. We're going to get into kind of a little bit more in that one and kind of expand upon it to what is called the Schrodinger model or the quantum mechanical model. So this will be our kind of, 1 foot deep into the quantum mechanics world. So you can tell all your friends that you're starting to study quantum physics. Very exciting stuff. So we're going to see that within a particular group of orbitals, the best one is going to be called, let's see, what color haven't I used yet here? Orange. The closest ones are called s orbitals. After that, we have p orbitals, d orbitals, and then these guys back here, the nosebleeds, these are f orbitals. I'll just write that here. And we're going to see that these particular orbitals are going to be energy levels within a particular shell of the nucleus. And so we're going to have to talk about a little bit of terminology going forward. So we have what are called shells within an atom. And those shells are going to be groups of orbitals. And what that means is, if we look back at our previous model, the Bohr model that you guys are used to seeing, and if you have, you've got your 2 electrons here, and maybe you've got, 5 electrons there or whatever. Oh, good morning. Nice to see you. These shells are basically the rings. And so in the Bohr model, you can just stick as many electrons that can possibly fit into these shells, and that's kind of how that model looks, right? So in this case, I have, if we're looking at this particular example, this atom has 2 shells that's signified by the 2 rings. We're going to talk about those shells as these are the 2 the shells that this atom has. We talk about them as n equals 1 is 1 shell, n equals 2 is another shell. So those are going to be the 2 shells that this atom has. And in this case, it looks like, just the way I've drawn it, we have 2 electrons in shell, in the n equals 1 shell, and then, let's see, 1, 2, 3, 4, 5. I've put 5 electrons in the second shell. So that's kind of how you can think about how these shells look. All right, and so one of the things that we're going to expand upon is this particular model that we may be familiar with. Model, by the way, I just mean like visual way of explaining atoms. So that's what I mean by model, by the way, when I say that. So this particular model, it's pretty good, but there are a few drawbacks because we're going to see, particularly in this second shell and going forward, that this model has those 5 electrons kind of equal energy, as in they're all just kind of in this circle around the atom. But we have learned more recently that those electrons are actually they will have different energies. And so it's important for us to describe those. So what this model does not have lacks what are called subshells. And so those subshells are going to be the S, the P, the D, and the F. So just like in our lovely concert here, the Bohr model, the rings around the atom, it kind of groups all of these concert seats together. So it says, okay, you're attending the concert, you're in this ring. You know, that's it. That's the end of it. And so maybe we have 18 electrons in this one ring around the atom, and that's it. However, with the quantum mechanics model, the Schrodinger model, we're able to see that these kind of seats at this concert do have different, like, you know, some are better than others, to say. Better being lower energy. And just so you know, an atom, or rather a shell, can only have between 1 and 4 subshells. And how that's going to work is we're going to have in the first shell, the n equals 1 shell, we're going to have only an s orbital, an s subshell. In the n equals 2, we're going to have an s subshell as well as a p subshell. And as we keep adding more shells, we're going to keep adding more and more subshells. And so we're going to see here 4s, 4p, 4d, 4f. They always come in that order, s, p, d, f. And so understanding that even if we have more shells, we don't ever go above 4. So we don't have anything beyond the f subshell. And then, just so you know, there's only 7 possible shells. Oh my goodness, 66F, and then 7S, 7P, 7D, 7F. Yikes. Okay. I'll tell you right now, some of these don't exist, but we'll worry about that later. So for now, or rather they exist, they're just not used. In ground state atoms, at least. So, these guys are all the possible subshells. And this one is, these guys are all the possible shells. And we're going to see that we can talk about these in terms of the periodic table. We're going to see that the shells correspond with the period. That's the row of the periodic table. So the way the periodic table is designed, oops, I'm such a good artist. Oh no, it deleted the whole thing. Okay. Boom, periodic table. And then we have our other dudes down there. Okay. Sorry, a little bit more artistry here from me. 5, 6, 7. Okay. Guess what? We have 7 periods within the periodic table. I am sorry that they're so crappily drawn, but trust me, there are 7 rows in the periodic table. Just so you know, you'll see that, you know, sometimes on the bottom you'll have those 2 rows. Those rows are just kind of taken out for space purposes, just because the periodic table would get too wide if we were to stick those in there. So technically, like, if we were to really draw it, the periodic table would look like this. We would have like all the way down there, Like technically this is what it would look like if we were to stick those two rows in there, but they decided, you know what, it's just a little bit easier for us to keep those up top. So just going to delete that because there's no sense in, okay, come on, really? There we go. Okay. So we're going to see that these rows of the periodic table correspond with the shells. And we also know a few more properties about these. We know that the maximum capacity of an S subshell is 2 electrons. A P subshell can hold 6 electrons. A D subshell is 10, and then the F is 14. These are maximum capacities. So any particular S subshell can hold 2 electrons. Any P subshell can hold 6, and so on. And just to throw another wrench into our this kind of glob of verbiage and new words, we have what are called orbitals as well. And the subshells and orbitals are very closely intertwined. I'm out of space here, but I'll just kind of write them. This glob here is the number of orbitals. And we're going to see what those look like in a little bit. And so if you look at these numbers, the SPDF numbers of how many electrons they can hold, and we also look at the number of how many orbitals there are, you can probably deduce that each orbital can hold 2 electrons. So, because if you have, for example, in a P subshell, you're going to have 6 electrons that can fit in there. Those 6 electrons are going to have to be divided within 3 orbitals. And so that tells us that we're going to have a maximum of 2 electrons per orbital. And by the way, I'm totally aware this is like, what the heck, what's the point of all this crap? You know, this is very confusing. I understand that. The way it is, unfortunately. So, with that being said, let's take a look at some particular atoms here. And let's see if we can't figure out what all this stuff means. Okay, by the way, of course, if you guys have any questions, throw them in the chat. So, let's, for example, take a look at lithium. If we know where lithium is on the periodic table, it is element number 3. In the ground state of neutral lithium, that's not a charged one, not an ion, it has 3 electrons, right? 3 protons, 3 electrons. We always want to give the electrons the lowest possible orbitals. And so if we see where lithium is on the periodic table, it is in row 2. And so that means, so lithium, I'm just going to write all this out, is in period 2, therefore has access to it has access to the first two shells. That's what the periods mean. So if something is in period 5, it has access to everything through n equals 5. So you always have the stuff that comes before, as well as where you are currently. So lithium currently has access to the N1 and N2 shells. So, thinking about that, we know that for the first shell, there's only one orbital in there, one subshell. In the second one, we have a 2s orbital, and we also have the 2p subshell. And so, if we understand, going way back, sorry to have to scroll all the way up, but the best one, the lowest energy, is always going to be S. If you have the option, S will be better within a particular shell. And then P, and then D, and then F. So I'll write that again down here. Let's see, how about green? Meaning this is like kind of the best spots. Okay, so S is going to be your best place to put electrons, and then P, then D, then F within a particular shell. So, considering this, one more thing we want to talk about is lower shells are always better than higher shells. Meaning that the first shell is better than the second, better than the third, better than the fourth, etc. And so, because we always want to give our electrons the best possible place, we want to make them happy. That's what ground state is all about. Okay, now let's look at this again. So we have 3 possible electrons, and we want to put them into the best possible spots. So we have options here. We know that s orbitals are more favorable than p, than d, than f. We don't even have d's and f's here, so skip them. Looking at these lower shells, though, we know that 1s is going to be our kind of best place to put electrons. And so let's go ahead and put some electrons in there. We must remember that a particular orbital can only hold a certain number of electrons, right? 1s, if we go back up, s orbitals can hold 2 electrons maximum. So let's go ahead and put 2 electrons in the 1s shell. And so we have 3 total electrons, right? We've now gotten rid of 2 of them. We have 1 left. So let's go ahead and put the last one into the next orbital. The way we describe this is we'll write it like this, where we have, this is the shell, this is the subshell, and then this number here is number of electrons in the subshell. So hopefully the color coding will work here. So for our lithium, we can describe the electrons of lithium in this manner, describing which shell the electrons are in, which subshell they're in, and how many are in that particular subshell. I know a ton of information, and again, the point is not obvious to you, but it will be soon. I promise you. Okie dokie. I'll let that absorb for a second. Does anybody have any questions so far? Alrighty. Not seeing anything. So, we can do this again. And after this, I'm going to show you a kind of shortcut way to get around this. So let's look at aluminum next. Aluminum has 13 electrons, if I remember correctly. So we're going a little bit crazier here. It is in period. Where is aluminum? Period 3, right? Yeah. Period 3 of the periodic table, which means it has access to n equals 1, n equals 2, and n equals 3 shells. So, remembering before that this guy only has an S subshell. N equals 2 has 2 subshells, and n equals 3 has 3 subshells. These are the options we have, and we always want to fill them from lowest to highest, right? So, looking at that, blue perhaps, we're going to want to start with our 1s shell, subshell rather. That's telling us, okay, we've used 2 of our electrons. Now remember, S can hold a maximum of 2. We're just going to want to keep throwing in electrons until we fill them up. The next one for us is going to be 2s. That's the next lowest. That one can also hold 2 electrons. So we have 9 left now. If we keep going, next is 2p. 2p, remember, p subshells can hold 6 electrons. So that's now 10 electrons we've taken care of. And if we keep going, we're going to see that this is where we're going to end up. If we add up all those numbers on the top, 2 plus 2 plus 6 plus 2 plus 1, that should be 13. And we're going to be able to describe these electrons later. Actually, we can describe them now. These ones are going to be called valence electrons. Those are going to be electrons in the outermost shell. Remember, the shell is the big number in the front. So those are called valence electrons. Oh, Oz just farted. Stinky. You'd think this little old man would have better manners, but no. Stinky little dude. What did you eat? Stinky, stinky. Oh. Nasty Oz. By contrast, we're going to see these ones are called core electrons. Those are more towards the nucleus. Those are going to be anything not in the outermost shell. Okay, and we're going to see that valence electrons are going to be where all the action is happening in chemistry. So we're going to be talking about valence electrons quite a bit. So just so we know, if we were to look at this aluminum atom, we're going to see that in this case, aluminum has 3 valence electrons. It has 3 electrons that are stored in its outermost shell. We know that by adding up these two guys. Those are how many valence electrons we have. So in this case, aluminum has 10 core electrons. We could add up 2 plus 2 plus 6. And it has 3 valence electrons. Because I should have written core first, but oh well. Alrighty. So I have 2 shortcuts for you guys for when we're coming up with what is called the electron configuration of an atom. First one, easiest way to look at it is I'm going to try and be very good with my drawing here. Wow, look, that almost looks like a periodic table. I did it. We're going to see that the periodic table, lucky us, is going to, I guess I forgot the last stuff on the bottom here. We're going to see that there are divisions we can make in the periodic table that are going to make our lives easier. We're going to see, hold on, 5s. Okay. These 2 rows are what is called the S block. That includes this helium over here. Just, you know, helium and hydrogen are kind of just stuck on top. We'll deal with that. We're going to see that here, gosh, these brackets are awful. This is what's called the P block of the periodic table. 3p, 4p, 5p, 6p, 7p. Here is called the D block. I'm going to omit writing in the D's right now. And then down here in Nowheresville is the F block. We're not even going to touch the F block in this course, so don't worry about it. So, if we were to consider the electron configuration for an atom, we're going to see that we can kind of just use the periodic table as a kind of quick way to figure out the configuration of a particular atom. So when we just did aluminum, aluminum was right here, right? And we were able to come up with its configuration. There it is up there. We're going to see that aluminum is going to start with 1s. It's going to go through 2s. It's going to go through 2p. It's going to go through 3s. And it's going to end here at 3p. So the last kind of spot in your electron configuration will match where it is on the periodic table. So let me just go ahead and write that down in dark blue. Any element will have its last electron in a block it resides in. So, for example, bromine in the P block, if you don't have your periodic table here, actually, no, not Discord. Don't need Discord right now. Okay, so understanding that, hey, let me just draw on this. No, I don't need professional. I need to draw. I think that's this button. Yes, screen right there. We go. Okay, let it do its thing. Okay, here we go. Bromine is right here. Remembering that this is the p block, this group of 6 columns. Notice p block can hold, or p orbitals, p subshell, sorry, can hold 6 electrons. Notice there are 6 columns here. Magic. Notice here in the s block we have 2 columns, and s subshells can hold 2 electrons. We have 10 columns in the D block for 10 electrons. And then we have, of course, the F with 14. So bromine here is going to be in the P block. So we know its last electron is going to be a P electron. Understanding that bromine is in period 4, we know that it is going to have its last electron in 4p. Okay, understanding kind of where it is on the periodic table. It's in the 4th period, so the 4th shell, and it has, it's in the p block, so p electrons will be the last one. So, oh man, why did I choose bromine? I should not have done that. Oh well. Too late now, huh? So it's going to have 4p as its last subshell. That's the last one we're going to fill up for bromine. And if we see where bromine is, it's the 5th column. 1, 2, 3, 4, 5, 6, right? There are 6 columns in the P block. Bromine is right here. So bromine will have 4p5 as its last electrons. And so what this is going to mean for us is that we just have to fill in everything before 4p. And so that means we're going to go through 1s, 2s, 2p, 3s, 3p. I'm going to stop right there and just put ... just because the next part will be confusing. We're going to just have to fill in everything. And what that means is we fill up to maximum capacity. And so we know our S subshells can all hold 2 electrons. The P's can all hold 6 maximum. We just have to fill in everything up to maximum until we get to where bromine is in the periodic table. Okay? Again, there is a reason we're doing all this stuff. So again, bromine in the P block, it's in the 4th row, which means it's going to have 4p as its very last subshell. And we have to fill in everything before that. Now, just to not confuse you, we remember that S is a better orbital to fill than P, than D, than F, right? Because S is low energy, and we're going to see F is high energy. We're going to see that, remember, same thing. that this was low and 7 was high energy. So we don't want to put stuff in 7 if we don't have to. Right? So, that being said, we can tell that 2s is a better orbital to fill than 2p, right? It fits both of these patterns. If we were to compare let's make this a little bit more obvious. What do we think about 4s versus 2p? Which one's going to be better for us to put electrons into? It may not be as obvious to us, but I'm going to tell you that we're going to want to put them into 2p first. It's not as obvious to you because, we know that... actually, no, this should be very obvious to you. No, it shouldn't. Okay, we know that p is worse than s. However, in this case, the number of shells is going to be the deciding factor. And for us, it may not be super obvious, but we have calculated these things in chemistry. Poor physical chemists have done all this work for us. And we're going to see that we have several ways of making these easier for us. Just to complete our periodic table here, I'm going to tell you that 3D is going to be right there on the periodic table. 4D, 5D, 6D. And so you're looking like, what the heck? We have 4s followed by 3D, like that doesn't make sense. It turns out that the 4s subshell is lower energy than 3D. So even though 3D is in a smaller shell, the fact that the s orbital has lower energy than a d orbital kind of overrides it in this case. And so that's always going to be the case for the s versus d comparison. The whatever the s is going to be better than the d of the previous one. And so we just have to remember that anything we're doing in the d block just is one shell behind. I understand this is not obvious to you, but that's the way the energetics work out. So 3D is actually kind of in between 4s and 4p in terms of its energy. And just to put this out there, although we are not necessarily going to touch it this semester, the F block is actually 2 levels lower. So 4F is actually going to be in between 6S and 5D, but let's not worry about the F block. I'm putting it there so it will be in your head somewhere for when you get to 111, but for right now we're just going to leave it as it exists and that's it. So that being said, if we follow this pattern and go back to our bromine example,